Okay. I think we're ready now. I think. Okay. So y'all know today is drop day, right? Today is the last day to drop with a W. Okay. So I have two things that I want to talk to you about before we start, but you will need the eye clicker. You will need your best friend. And you will need a calculator, not for the eye clicker questions, but for class. So take out your calculator, take out your best friend, and we'll do eye clicker in just a second. So I'm going to show you a few things real quick on the Moodle site, right? Okay, so you'll see that we have, let me close them all, close all, right? We see our different topics on our Moodle course. So we're in Unit 4, chapters 8 and 9. So we're finishing up the material for our last exam, which is when? When? Tuesday. So 1 week from today, Tuesday. But at the same time, you kind of need to be thinking about the final exam, right? The final exam is different for 4T and 5T. Y'all are 4T. So 4T, it will be Wednesday, December 15th from 1 to 3 p.m. Okay. How do you practice for the exam? The final exam is cumulative, semester cumulative. So every single thing that we have covered in this class can be on the exam. It's a lot of material. So what I did for you is I put together some practice questions for you. Are these questions going to be on the exam? No, they're not. But these are similar to the types of questions that you'll see on the exam. Could there be things that are not on here that are on the exam? Sure. This is just some good practice problems for you, right? If you've done all the practice problems at the end of the chapters, you know, like you just need some more practice. So this, let's see, we are not, come on, if I can make this bigger. We're only doing chapters 1 through 9. We did not get to chapter 10 because of Hurricane Ida. So you will not see any material for chapter 10 on the final exam. Usually we do cover it, but Hurricane Ida happened, right? Okay, so there are practice exam questions, and then I posted all of the answers. So what I would do is I would print out the questions and try them, and then go and check your answers, okay? Good on that? All right. The other thing is that there is going to be a group review with the Tutoring and Academic Enhancement Center, and I sent them all of this review material, so they have it. So I don't know exactly what how they're gonna run it, but they have all of the material that y'all have, right? And the review will be Thursday, December 9th from 4 to 6 p.m. in the library. But I heard it's pretty good. What is that? I don't know. Okay. What did I click on? Course, right? Come on. Okay. The very last thing is, if you look on Moodle, there's a little last section that says extra quiz. Okay. This, why is it not showing? Oh, really? It really should be showing. Hold on. Let me go back to my instructor mode. And let me see if I can show it. Come on. Moodle. Me and Moodle don't always get along. Okay, so let's try refreshing this. Do y'all see it? Y'all log in? No? I don't know what's going on with the internet today. But it's going to count for a homework grade. If I can get over there. Okay, so I'm the instructor. Oh, because it's hidden. Why is it still hidden? Let me unhide it. Show. Good. Okay, So let me explain a little bit about this real quick. So this extra quiz, I'm doing some research on learning. And so I'm asking you guys to be participants in my research study. So whether or not you participate is up to you, but it is required that you take this quiz right here, whether you choose to participate or not. But the more people who participate, the more we can learn, the better instructors we can be. Like, we really want to learn things, and I can't tell you exactly what the research is about because that would spoil it. So I can't tell you exactly what we are researching, but all the information on the research is here. This is the consent form. So if you agree to be in the study, then you have to sign the consent form saying, yes, you're okay with it. But then whether you say yes or no to the consent form, you take the quiz. Now the quiz is due Friday, December 10th at 9 p.m. On average, it's taken people about 20 minutes to do, but some people take up to 45 minutes. That's kind of like the longest we've seen people ever take it. So when you sit down, you have to do it all in one. Now, there are no right or wrong answers. So if you do it, you get full credit. If you don't do it, it's 0. This is a great way to boost up your score a little bit at the very end, okay? So this quiz is required for everybody, done or not done. You can't get them wrong, okay? And if you have trouble filling it out, you know, like the initial part, let me know, I'll help you. But it's just done or not done. No big deal, okay? Questions? Everybody good with that? All right. Okay, so now, y'all ready for, and I don't think I opened it. Oh yeah, I did, ha ha ha. All right, for iClicker questions, you, full screen. All right, here we go. Y'all ready for this? Yeah, y'all got this, you're good. All right, remember you can have your best friend out. Select the strong electrolyte. Select the strong electrolyte. Remember what a strong electrolyte is. It's not too bad to figure it out. Give y'all another 30 seconds on this. I see a lot of people still thinking. So 1.5 minutes. Okay, 10 seconds. Take a guess. Okay, now turn and talk. Try again. I can talk to people far and wide. It's all good. All right, 45 seconds. So don't forget to click in again. Got 5 seconds. Don't forget to click in again. Okay. So what did we say? What did we say? Okay, B, good, good. All right, so let's talk about this. Oh, let's talk about this. How do we know if something is a strong electrolyte? What's the definition? It dissolves and disassociates. 100%, right? That's the strong part. If it's a weak electrolyte, it only partially disassociates. So what are examples of things that are kind of in this list over here that are strong electrolytes that are in the chapter we're talking about? What chapter are we in? Acids, bases, and buffers. So you can have things that are strong acids or things that are strong bases. Those are what? Examples of strong electrolytes. So the only question you have to ask yourself is one of these answer choices strong, right? So if you look at A, what is A? Magnesium hydroxide, right? The OH, this is the hydroxide. So this is a base, but is it a strong base or a weak base? What's the rules? What do we look for strong bases? Acids, bases. What about bases? Group 1, or there are few in group 2. What are the few in group 2? The 3, it's 3 together on there. Calcium, strontium, and barium hydroxides. Right? Remember this? Yeah? Okay. So A, is A one of these? These are the strong bases. Is A one of these? No, it's in group 2, but it's not calcium, strontium, or barium. So what is A? That's a weak base. So it can't be A. KOH. What group is that in? K is in group 1. It's potassium hydroxide. That's a strong base. Ooh, very nice. NH3. What did I tell you about NH3? This was something you just had to know about NH3. It's a weak base. That was one I just said, put off to the side, and you need to know that one, right? Remember that? Yeah? Okay, HNO2. This is a what? Is this a base? This is an acid, right? That hydrogen can disassociate. So do I have 2 more hydrogens than oxygens? 2 more, I'm sorry, 2 more oxygens than hydrogens. Is that what I said? No, I don't. So this is a weak acid. So can it be D? Can it be C? No. And it can't be all of the above. Yeah? Can you do that in the future? Probably will have to. Okay. So remember how we said NH3 is a base? Remember how I said you need to know that? NH3 is a base. If NH3 is a base, by definition, what does it have to do? Think about our definition, our Bronsted-Lowry acid-base definition. What does it do? Okay, 10 seconds. Okay. Turn and talk to the people around you. Remember, 45 seconds. Okay, 5 seconds. Make sure you click in again. Don't leave it blank that second go round. Okay, so what did we say? Good, good. Oh, and we went up, awesome. Okay, so if I were to take NH3 and put it into water, what would happen? What would happen? We said it's weak, so it's got to be that reversible reaction, right? What would happen? If you told me it's C, it accepts a proton from water, right? That's what you told me it was. What does it do? What happens? What's my end result? Am I NH3 anymore? No, right? What am I? NH4, and it's positive, positively charged. What am I left with? A hydroxide. This is why we call it a base. Because when I put it in water, I get hydroxide ion. That's why it behaves as a base, right? It doesn't look like it. It doesn't have the OH. It's not like NaOH, right? But it still is a base. So it starts off here, right? This is the base. And what does a base do? Accepts a hydrogen ion, right? Okay. Yeah. All right. One more. Let's see what we got. All right. So according to our same theories, when an acid is dissolved in water, it does what? Okay, 5 seconds. Make sure you click in. All right. So turn and talk. Come up with a second answer. Okay, 45 seconds. Don't forget. Okay, so what did you say? Let's see. Okay, so we're pretty split. We're pretty split between C and D. Well, so I'm really happy that y'all were able to eliminate A and you were able to eliminate B, right? Because we know an acid does what? It must donate a proton. So that part of your answer is correct. And we know why is E wrong? Pure water, right, is neutral. So we don't need that. Okay, so the question is, if you start with something that's an acid and you put it in water, what does it make? Well, if you have something that loses a hydrogen, so just say HX, right? Doesn't matter what it is. We're going to put it in water and we're going to form something. What's going to happen? What are we going to form? Our hydrogen's going to come off. What am I going to be left with? X minus whatever X is. And then what am I going to be left with here? H3O plus, right? We talked about that. So if we have something that starts off here as an acid, right? When we go from left to right, what's happening? We lose or we donate a proton. Now, do I still have an acid? No. What happens if I take this and I go in the reverse? What am I doing? I'm gaining what? Or accepting a proton. What's the definition of something that gains a proton? That accepts a proton? It's a base. So an acid donates a proton and forms, and we call it now a conjugate base, but it forms a base. So it should have been C. It should have been C. Okay, let's go to our in-class problems, which I don't even know if I pulled up. I think I only pulled up one. Oh yeah, I didn't like it. No, I'm just gonna try again. Okay, I think we ended on 9.18, is that right? So complete and balancing balance the following neutralization reactions. This is one we left off on, correct? Yeah, okay. So when we do this, what's happening? We have H2SO4, it's aqueous, plus NaOH, this is a solid. In any neutralization reaction, what do we make? Always, 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 always. I know it's been a Thanksgiving break, but what do we make in a neutralization reaction? Water and a salt. And sometimes what? If we have carbon, CO2. Okay. So where's our water coming from? Let's do that first. So I have an OH here. What do I need from the other side? I need one hydrogen, right? So I'm going to take one hydrogen away from H2SO4. And I'm going to make HOH or H2O. What's the state of matter for water? It's a liquid. Okay. Now, what's left over? I have one hydrogen in the SO4, right? So we have to figure out what's going to happen to that other hydrogen. So let's keep that in our back of our minds that we have that other hydrogen, but we also have SO4 and we have Na. So can I make a salt with that? What's a salt? a metal and a non-metal, or what? A metal and a polyatomic ion, or two polyatomics, right? So can I make a salt with what's left over in blue? What's the metal? What's the metal? Na or SO4? Na. Na, sodium is the metal, okay? Now, SO4. Can I just write NaSO4? Why not? Get your best friend out. Go find your polyatomic ion of SO4. What's the charge on SO4? SO4 is 2 minus. What is Na? Plus 1. So if we crisscross them, that's a 2 and then a 1. Do we have to write a 1? No, so it would be Na2SO4. So I'm going to write that, Na2SO4. Now, am I balanced? No, because remember I had that tricky thing with the hydrogen, right? So I actually have to worry about that in my balancing. What could I do to fix that when I balance this chemical equation? If I take 2 hydrogens from H2SO4, how many hydroxides would I need? 2. Right? How many waters would I make? 2. Now am I balanced? Now I'm balanced, right? And it also took quick care of the Na too, right? Because if I look here, I have 2 sodium atoms here. And before I put the 2, I only had 1. But now that I have the 2 there, I have 2 and 2, so I'm good. If you keep track of how the water is formed, it makes balancing the equation easier. You could do it atom by atom, like we've done in the past. You could absolutely do that, but it would just take you a lot more time. Yeah? Okay. Can I erase this one so we have room for the next one? All right. So are we going to make carbon dioxide with our next one? No, because we don't have any carbon. Okay, this is a neutralization reaction. So I know I'm going to make water. Where does the water come from? H, 2 hydrogens and an oxygen, H2O. So I'm going to make H2O. Water is a liquid. And then what else do I have left to make? My salt, right? My salt. So where does my salt come from? I need a metal and a non-metal, or a metal and a polyatomic, or 2 polyatomics. So here lithium is a metal, right? And bromine is a non-metal. So I could have lithium bromide. Ooh, I don't think I put state of matter. What was the state of matter? Here. And on the previous one, the salt in the previous one. Aqueous. Are we balanced? And can we write LIBR like that? Lithium has a charge of +1. Bromine has a charge of -1. So you crisscross, it would be Li1, Br1, but we just don't write the ones. So now, is my chemical equation balanced? Yeah. So am I good? Absolutely. Okay, good. All right. So when we talk about things being strong acids and strong bases and weak bases, what we're really talking about is called chemical equilibrium, right? So remember when we had something that was NaOH, is that a single arrow forward or is it a forward and reverse? What group? I'm in group number 1. So this is a strong base. So if I put this into water, what's going to happen? It's going to just disassociate. So I'll have Na plus OH minus, right? So it's a 100% disassociation. But not all reactions proceed to 100%, right? We've seen that. We've seen that in any equation where we have this double-sided arrow, right? What does that double-sided arrow tell you? You're making some products and you still got some reactants, right? But the question is, how much of each, right? The more product you make, if it's an acid or it's a base, the more product you make, the stronger the acid or the stronger the base is. Until you get to the most extreme where you have no more reactant left and you've got all product, right? That gives you the strongest acid or the strongest base, but there's lots of in-betweens. And so what we'll talk about today is how to figure out the in-betweens. So you have to kind of understand chemical equilibrium. So we know that a reversible reaction can go forward and it can go reverse, right? But when does a reaction reach what's called an equilibrium? And before we answer that, we have to say, what is an equilibrium, right? So y'all are gonna have to help me, but I'm gonna make a sports analogy. Okay? If we're gonna play football, right? How many players are on a football team? A bunch, right? Like 50. There's a bunch of, not everybody plays, but how big is the team? It's really big, right? Even I know that. I don't know that much about football, but I know that. Okay, how many players are on the field? Anybody know? Help me, please. 11? 11? Yeah? Close? Okay, good. All right, so then how many are on the bench? 50 minus 11. 39 are on the bench. Okay, so the team is like saying we have products and reactants, right? The field is one of them. Let's say it's the products and the bench is the reactants, right? So when a reaction reaches equilibrium, you have an equal number of players who are leaving the bench to go get on the field as you do players coming off the field to go sit on the bench, right? In any sports game, football, baseball, basketball, you can only have a set number of players on the field, right? And it varies per game. Same thing is true in a chemical reaction. You can only have a set number of players who are reactants and a set number of players who are products. And it varies for each reaction how many there are. Does that make sense? So when does a reversible reaction reach equilibrium? So it reaches equilibrium when you have an equal I'm going to say equal rate of formation of products, right? So the rate of formation of products, is that my arrow forward or my arrow in reverse? I have a chemical equation that goes reactants to products. So this is my forward direction arrow. So when we have an equal rate of formation of products as rate of formation of reactants. Does that mean I have an equal number of atoms in the reactants as the products? No, because if you look at that football field, I don't have an equal number of players on the field as I do on the bench. And it'd be different if we were playing basketball, right? If we were playing basketball, how many basketball players are on? It's less, right? 5? Something like that, 5. Okay, so you can only have 5. Y'all, I'm sorry. You can only have 5, but you can still have a lot of players on the bench. But if you sub one in, somebody else has got to get off the court, right? It's the same thing. You don't have an equal number of reactants and products at equilibrium. Everybody wants to say that. And I promise you that there will be something on the test where one of the answer choices will say, at equilibrium, you have an equal number of reactant molecules as you do product molecules. Is that true or false? That's false. It's the rate of formation, the rate at which you're making product and the rate at which you're making reactant is equal. And that's kind of a difficult concept to think about, but we're going to continue to work on that. Okay. So whenever we're talking about equilibrium, the way that we say that is just a ratio, because it doesn't really matter technically if I have 10,000 atoms of this and 500 atoms of that, right? The number isn't really important because the reaction would happen if I had this massive reaction or if I had this teeny tiny reaction. It would still happen. So what we do is we look at a ratio. So we call this the equilibrium expression. So this is my equilibrium constant. So it doesn't matter how big or how small my reaction is going to be. For any given equation, K is going to be the same for that reaction. So for example, A, if I did this reaction in a teeny tiny vessel, K would be the same as if I did this reaction in a vessel the size of our classroom, right? It'd be the same value because the ratio of products to reactants is always going to be the same. So the way that we express this is we always put reactants over products. I'm sorry, we put products over reactants. Why did I completely say that? So always put the end on the top. So products go on the top, reactants go on the bottom. And so when I wrote this, I wrote these brackets. What do the brackets mean? What does a bracket mean? Concentration. Because whether I had this tiny, tiny vesicle, this vessel that had my reaction going, or I had the whole classroom, the concentration ratio should be the same. Okay. So when I do this, I need to take into account all the reactants and all the products whose concentration can change. So if I'm a gas, if I'm aqueous, I can change. But if I'm a solid, does my concentration change? No, it's just a solid. So you don't take into account solids. What's the abbreviation for solids? S. And then liquids. Like if I have liquid water, are you going to change the concentration of the water? No, it's just liquid water, right? So you don't take into account solids and liquids. So when I evaluate a chemical equation, I look for my solids and I look for my liquids and I cross them out. So in A, do I have any solids or liquids? No, so I'm going to include them all. So if I want to know my equilibrium expression for A, I need to put my products on top. So here are my products. Everything on the right side of the arrow is a product. So I would take the ratio of the concentration of NBr3. Now, and when I look at that NBr3, what do you see in front of it? A 2. It means there's more NBr3 than there is N2, right? That's what a balanced chemical reaction is telling you. So you have to translate that to the equilibrium expression. So anything that was a coefficient becomes an exponent. Becomes an exponent. So I'm going to take that and I'm going to put a 2. So I can take that balancing into account when I have my equilibrium expression. Now, what are my reactants? I have my concentration of N2. Do I put that as a subscript? Where do I put that 2? It's a subscript. It's telling you about the substance. Okay, now you have to multiply if you have more than one reactant or product, right? So in this case, we have N2 and we have Br2. So we're going to multiply the concentration of N2 times the concentration of Br2. But what am I missing? The exponent. So this is my equilibrium constant expression. Now, you won't have to do the math, like you won't have to put in the concentrations and calculate it. But we're going to look at what happens when we get a value for K and what that means. So for right now, let's just practice writing the expressions. So let's try B. Here's B. K is the same thing. It's our concentration of our products over concentration reactants. So what are my products over here? I only have one product, right? What's my product? CO2. Now, I'm going to divide that by my reactants. Here are my reactants. What's the first thing you should do? You should look at them and you say, oh, I have a solid there. So it doesn't change concentration. It's a solid. So you don't take it into account when you do the equilibrium expression. So we only have one other reactant, and that reactant is O2. Not too bad, right? So it's just recognizing those solids and those liquids, and you'll be okay when you write those. All right. So now what we want to do is we want to understand what does that mean? If I am going to get a value for K, what does it mean? Well, if you understand the relationship, right? K is equal to our products over our reactants, right? If you take a numerator and divide it by something, right? If the number on top is bigger, so if P is bigger, what happens to K? It gets what? I hear it, say it. It gets smaller. K gets smaller, right? That's saying like you have 10 divided by 5, right? What would you get? 2. But what if the opposite were true? What if we said, I want to have that. What if we said 5 divided by 10? So in this case, if R is bigger, what happens to K? It gets what? Even more tiny. So what do we get? 5 divided by 10. Put it in your calculators. What's 5 divided by 10? 0.5, right? All we did is move a decimal place. So if you look at this and you mathematically do many, many, many of these, we can come to two conclusions, right? We can say anytime here, if P is greater than R, which one is that where P is greater than R? Down here, right? If P is greater than R, then K is greater than 1. It's always going to work out. It will always, 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 always happen that way. Now, if the reverse is true, if R is greater than P, so let me do this in a different color. If R is greater than P, so R being greater than P was our second example here, right? What did I get? I got a value that was greater than 1 or less than 1. K is less than 1. It'll always, 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 always happen that way. Always. So if you look at the ratio, it can tell you whether you have more products or you have more reactants present. So look at A. 1 times 10 to the 7th. What is that in non-scientific notation? 1 and how many zeros behind it? 3, 4, 5, 6, 7 zeros. So that's 10,000 million, 10 million. Is that greater than or less than 1? K is greater than 1. So if K is greater than 1, what do I know about my ratio of products to reactants? I have more what? If K is greater than 1, I have more products. I have way more products. More products. Do you see that relationship? If you just know this and the math, you got it. But if you don't quite understand the math, then you just kind of have to memorize this part. Okay, look at the next one, B. Is B greater than 1 or less than 1? Less than 1. So this is a K value that is less than 1. If K is less than 1, which one do we have more of? More reactants. Now, I want you to rewrite C in scientific notation. What should it be in scientific notation? (7.9) times 10 to the -7. So if you have something with a negative exponent, what does that tell you? It's less than 1. So here, K is, again, less than 1. So sometimes you'll see it typed out, and sometimes you'll have to evaluate it in scientific notation. So you have to be able to go back and forth, right? So if K is less than 1, what do we have more of? More reactants. Okay? Practice, 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 practice. Okay. So why is it important how much of something is present in a reaction? Well, we can use the concentration of reactants or products to drive reactions, to make things happen. Like, what do you want to happen? I want this reaction to go to products. I want that one to go to reactants. I can make that happen. Like, you feel very powerful, right? So here's an example reaction, right? We have lead-2 iodide can be produced upon cooling lead-2 and iodide ions from a solution. So this is my solution. These are my reactants, and I am making these as products, right? So the question is, what happens if I alter this reaction? What happens if I change this reaction? So A through D is telling you, these are the things that I am going to do to the reaction. And then I want to know, how will that affect the chemical reaction? What will happen? So I want you to kind of think about answering this in two parts, okay? So part one, we're going to say, what did we do? And part two, we're going to say, what did the reaction do? So this is what we did, and this is going to be what the reaction did, okay? So A, we're going to add the iodide ion. So if we add the iodide ion, we are increasing a reactant or a product. Where is the iodide ion? Is it a reactant or a product? It's a reactant, it's right here. So if we increase a reactant, what's going to end up happening is that that's going to shift the whole reaction to do the opposite. So whatever we do, the reaction is going to accommodate that push by doing the opposite. So if we increase reactants, what is the reaction going to do? Decrease reactants, right? We increased reactants. So we put more iodide ion in. So what's the reaction going to do? The reaction is going to use up that iodide, and it's going to make what? It's going to make more product. So the question asks us, in which direction will the equilibrium shift? Will it shift left or will it shift right? So if you decrease products, what kind of a shift is that? I'm sorry, what I said, what if you decrease reactants? If you decrease reactants, this is what the reaction is going to do. If we have less reactants, which way is this equation going to shift? To the products, right? So you just have to think about what's happening in the equation. So this is going to be a left, right. I got to think about this. A right shift. Okay, try B. Look at B. Heat the reaction. If we heat the reaction, you got to look at the reaction and see where is heat in this equation. Reactant or product? It's a product. So we are increasing a product. So what's the reaction going to do? It's going to do the complete opposite. It's going to decrease a product. How do we get less products? How do we get less products? Make more reactants, right? So what kind of a shift is this going to be? This is going to be a left shift. Try C and D. Take a minute. Try C and D and do it in the same way that we're doing it. Once you get it, turn and talk to the people around you. See if they got the same thing. Turn and talk. It's okay. You can talk. It's okay. Just don't lower your mask to talk. Keep those masks up. Okay, so what do you get for C? What did you do to the reaction to stress it? What did you do? You remove lead 2 iodide. Is lead 2 iodide a product or a reactant? It's a product. So we removed it. Did it go up or down? It went down. So the reaction is going to do the complete opposite. What's the complete opposite? Increase products. Make products. How do you make products? Shift what way? Make products go this way. So this is a right shift. Did I get that? Okay, so what did y'all say D was? A right shift. Let's talk that out. That's right, a right shift. So cool the reaction. So go find heat. Heat and cool, it's really the same thing. So go find heat. Heat is a what? Heat is a product. Are you increasing the heat or are you decreasing the heat? Cool means you are decreasing the heat. So if you decrease the heat, you decrease a product. What's the reaction going to do? Increase product. So this is why in chemistry, if you're trying to make things, you control the temperature. You can drive reactions to happen or to go in reverse, whatever you want, right? It's really cool. Really cool. Okay. Did I not see this on the video? Did I do 9.27 on the video? No, I didn't. Okay. Remember to, what's that? Okay, so in the lower atmosphere, oxygen's converted to ozone, right? You know the ozone layer, right? Y'all know about this? It's getting smaller, but it's actually getting a little bigger now. And that reaction occurs because of lightning. That's where our energy comes from. So the lightning gives you the heat that's required for this reaction to occur. So we have our oxygen that is normally O2, but when we convert it to ozone, that's now O3. So in which direction will the equilibrium shift, left or right, if the following changes occur to the reaction at equilibrium? So I want you to do the same thing. Take a minute. You can do it with the people around you, but say, what do we do? What does the reaction do? And then what is the shift? So try it. Try it. And you can talk while you do it. It's okay. Okay, y'all ready? Or need another minute? Another minute? Okay. Some people need another minute. Okay, y'all ready? Yeah? Okay, so on a side note, is this an endothermic or an exothermic reaction? This is endothermic. How did you know it was endothermic? Because it requires an input of energy, see, that's right. It requires an input of energy, in this time in the form of heat, to make the reaction go. The previous reaction where heat was a product is an exothermic reaction. Good, good. Okay, so we add O3. O3 is a what? It is a product, right? So if you need to label it, say, okay, these are reactants, these are products, right? So did we increase or decrease the product? We increase the product, so the reaction will decrease product. How do you lose product? You shift it back and make more what? Reactants. So which way are we shifting? Left. Okay. All right. B, we're going to add O2. O2 is a what? Reactant. Are we increasing it or decreasing it? If we increase reactant, the reaction will do the opposite, and it will decrease our reactant. So if we want to make less reactants, what are we going to do? We're going to make products. So we're going to go in this direction. So this is what kind of a shift? A right. Okay. Raise the temperature. Temperature is a reactant or a product? It's a reactant. Are we increasing it or decreasing it? Increasing. So the reaction will do the opposite. So it will decrease our reactant. How do we decrease reactant? Make product. So we're going to go to the right. Yeah, how are we doing? I'll get them right? Okay. Lower the temperature. So temperature is still a reactant, but in this case, we are lowering the reactant. So now we're going to do the opposite. We're going to increase our reactant. How do we increase reactant? Oops, trying to erase it. To make more reactant, we're going to shift left. Y'all doing good on that? Good, very good. Okay, so last one, let's do it. Let's do the same way. So make yourself a little table and y'all try it out. And then we'll just check. I think y'all got this, right? This is what we do. This is what the reaction does. And this is our shift. I'm not very good at drawing straight lines, if you can't tell. At least not with this program. So I'm going to label my reactants, label my products. So for A, heat is a reactant or product? Heat is a reactant. We're going to add it, so it's going to go up. So the reaction will do the opposite. We'll decrease reactant. What kind of shift? Is a right shift. Good. Okay, lower temperature. So this is just the complete opposite. It's still a reactant, but we're just lowering it. So now the reaction will do the opposite and increase. So now what kind of a shift will we have? And left. It's just the opposite. Okay, remove CO. CO is a product and it's going to go up or down. It's going to go down. So reaction is going to do the opposite. We're going to increase product. How do we increase product? By shifting to the right. Okay. Add water. Water is a reactant. We're going to add it, so it's going to go up. Our reaction is going to do the opposite. It's going to go down. So if we want to decrease reactants, we're going to shift to the what? To the right. Cool. Okay, so let's apply this to something in the body, right? This was really cool. I was really happy to do this one with the soda can. I really like that. But okay, so you're exercising, right? Now, if you just walk somewhere, are you breathing heavy? No. But if you do a sprint to that same place, what are you going to sound like? What am I going to sound like when I get there? Right? I'm going to be breathing really fast. Why are we going to be breathing really fast when we get to our destination? So we know that this is the equation for cellular respiration, right? So in cellular respiration, our bodies use glucose. This is glucose and oxygen to make energy in the form of ATP. And then as waste products, we make carbon dioxide and we make water, right? This is what you've seen in biology, right? So the more oxygen, the more glucose we consume. In order to run from one place to another, are you going to use more glucose, more energy, or less energy than if you walk? If you run, you're going to be using what? More energy. So you're going to need, if you run, you need more energy, right? ATP. So I'm going to be using up my ATP. My energy is going to be gone, right? Because I'm running, I'm expending it. So I will lose, so I decrease what? I'm going to decrease a product. If I decrease this ATP product, right? What effect is that going to have on the other side of the equation? If I make tons, I need energy, I need ATP. So I'm going to make a ton of ATP and use it up, right? I had to run, I had to make a ton of ATP. What happened to my oxygen and my sugar? They decreased, I lost them, right? They went away. So I've used up my sugar and oxygen. What happens if you run out of sugar and oxygen? You will, guess what? Pass out. So instead of passing out, what does your body do in response? It makes you breathe faster, right? Because if I'm running out of oxygen, how do I get more oxygen? Take a big deep breath, right? So that's why you run, when you exercise heavy, you're depleting your reactants. And so you breathe to replace them. So I've used up sugar and oxygen and I breathe more quick, breathe, B-R-E-A-T, breathe more quickly to replace the oxygen. Because theoretically, you're going to use up your oxygen before you use up your glucose. But if you end up using up all your glucose, you will pass out. You know, it's like people who don't eat and then they go exercise. You're going to pass out. Don't do that. Don't do that. Okay. All right. So now we have to talk about how all of this equilibrium stuff relates to acids and bases, right? So remember we said our equation for an equilibrium expression is our products over our reactants. I would put that like, this is one of those things that you need to know so that this is a memorized one, right? So that you can keep that right on hand, really quick to recall. So when we talk about the equilibrium expression of acids, we just put a little A here. The Ka is the equilibrium constant for an acid. So look at table 9.6, Ka values for substances acting as weak acids. Guess where you have this? Do you have this table on your best friend? Oh, very nice, right? But what is it missing? It's missing something. It's got all three columns, but what's it missing? This little arrow here. This little arrow tells you that as you go up the table, you have increasing acid strength. So what is the strongest acid on this weak acid table? The hydrogen sulfate ion. What is the weakest acid on the table? Water. Can you remember that water is weak? If you can do that, then you don't need the arrow, right? But the other way to look at that is to look at these Ka values. So look at the Ka value for water. 1 times 10 to the negative 14. That's 0 point, and we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. That's the Ka value. Is that Ka value greater than 1 or less than 1? It's much less than 1, right? So if we look at this, tell me, what do I have more of, reactant or product? Way more reactant, right? So if I have water, how much of water is actually going to turn into H plus and OH minus? A lot or a little? A tiny, 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 tiny amount is going to turn into the ions. Tiny, just a fraction, just a little bit, right? But if I look at my hydrogen sulfate ion, HSO4, that's 1 times 10 to the minus 2. 1 times 10 to the minus 2. More of HSO4 is going to lose that hydrogen than water. So it makes it a stronger acid. They're all still weak, but hydrogen sulfide ion is a stronger acid. Okay? So I'm not giving you this arrow. Do you realize that? I'm not giving you this arrow, but you know that water is weak. So you can answer anything knowing that. So look at these tables and identify the stronger acid in the pair, HCN or H2CO3. If something is a strong acid or a strong base, it's going to trump, right? But if they're both weak, you have to go to the table. So we're going to look for HCN. So HCN is right here, hydrocyanic acid, and H2CO3. H2CO3 is carbonic acid. So out of these two, which one is stronger? Carbonic acid, H2CO3. How did you do that? You just got it off the table, right? If you can read the table, you've got your answer. You just have to know how to read the table. Okay, and I wrote over the other answer. Okay. H3PO4 or H2PO4 minus. So we have H3PO4 is right here. Erase these other arrows. H3PO4, and then we need H2PO4 minus. So we're comparing phosphoric acid with dihydrogen phosphate ion. Which one is stronger? Phosphoric acid, right? Because it has the larger Ka value. So phosphoric acid. So is that the H2 or the H3? Be careful with that. It's the H3. Okay. HCl or HSO4 minus. Where's HCl? I don't see it on my table. Where's HCl? HCl is way over here in my common strong acid. And what am I comparing it to? HSO4 minus. So where's HSO4 minus? Right here. So what's stronger, a strong acid or the strongest weak acid? The strong acid. The strong acid trumps. You don't even have to compare anything. The strong trumps. Okay, not too bad. All right, so now when we do these next ones, all you have to do is just what we did at the very beginning of the chapter, where we identify the acid, we identify the base. But remember in the iClicker questions, we said, what happens to that acid when it loses its hydrogen ion? What does it become? The conjugate base. So look at A. H3PO4 turns into H2PO4 minus. What happened? It donated a proton. If you donate a proton, what are you? If you donate a proton, if you go from having 3 hydrogens to having 2 hydrogens, what are you? What? You're an acid. Now, when we go to H2PO4, are we now an acid? No. Now we could go in the opposite direction and pick up a hydrogen. So what are we? We're a base, but we don't just call it a base. We call it the conjugate. So when you compare an acid and a conjugate base, the difference is 1 hydrogen. Difference is 1 hydrogen, right? So do the same thing with water. What's happening to water? Water is accepting, right? So what do we call something that accepts a hydrogen? A base. That base turns into a conjugate acid. Okay. All right. See y'all next time. So we got all the way. What you got? Oh.
Wanting to stay in.